Today we are walking through Continuous Latent Diffusion Language Model, a paper about generating text by planning in a continuous latent space instead of committing to one token at a time from left to right.
Give me the big picture first.
Most language models generate by the arXiv rule predict the next token, append it, then predict the next one. That has scaled extremely well, but it fixes generation to a left-to-right order and makes global planning indirect.
So alternatives already exist, but they still leave something unresolved?
Right. The paper says existing non-arXiv or diffusion-style language models have trouble getting three things at once: efficient generation, scalable representation learning, and strong global semantic modeling.
What is their main move?
They propose CoLDLM. It separates text generation into two jobs. First, a text VAE learns a continuous latent representation of text. Then a diffusion transformer models a prior over those latent tests. The workflow diagram is the best place to see the division of labor.
On this workflow, should I read it as three separate stages?
Yes. Stage 1 teaches the VAE a stable text to latent unlatent to text mapping. Stage 2 trains the diffusion transformer on those latent blocks while controlling gradients so the latent space does not drift wildly. At inference, the prefix is encoded, response latent tests are generated block by block, and the decoder writes the response.
What is the VAE doing that a normal token model would not do?
It creates a continuous space where a whole piece of text can be represented before the final words are chosen. The paper stresses that this is not just a soft version of tokens. The latent is supposed to carry global semantic information, while the decoder handles local wording. The displayed objective shows why the VAE is still constrained during joint training.
What should I take from that loss without getting lost in the notation?
It keeps three pressures on the latent space. The reconstruction term says the decoder must recover the text from the latent. The KL term regularizes the latent distribution. The mask loss discourages the encoder and decoder from hiding everything in brittle surface details. That matters because the diffusion transformer can only learn a useful prior if the latent space stays meaningful.
Where does the diffusion part differ from token level denasine?
The paper frames the difference as prior transport. Token denasine tries to recover observed text-like states. CoLDLM uses diffusion to move noise toward a useful latent prior, then lets the decoder produce the actual tokens. So global organization and local wording are deliberately separated. Now the key question is whether the latent space really carries global semantics. The paper tests this through time step shifts on latent dimensionality.
Why does a shifting best time step say anything about global semantics?
If every latent dimension carried only independent local information, changing the number of dimensions should mostly rescale performance, not move the best noise level. But the best shift moves from about 1.0 at dimension 16 to 1.7 at dimension 64 and to 2.3 at dimension 128. The heat map shows the same trend across LA, MBADA, MMLU, SIQA, and the task average.
So the latent dimension changes both capacity and the useful denasine scale.
Exactly. The paper also reports that the average score rises from 8.7 at dimension 16 to 11.3 at dimension 64. And to 11.8 at dimension 128 under the same compute budget. Bigger latent tests help, especially on MMLU and SIQA. But the authors still say dimension alone does not solve latent space collapse. The result panels then compare several ways to train the latent space.
Which curve is the important comparison here?
The orange joint DTX1 curve is the main success case. It starts close to the fixed VAE baseline at low compute, but improves more steadily as FLOPS rise and ends above the fixed VAE, the weakly trained joint DD variance, the all-scratch setting, and the interval baseline.
Does the same pattern show up beyond the average score?
Yes. On LAMBADA, the jointly trained diffusion latent model ends highest, while the all-scratch and interval baselines stay far lower. That supports the paper's point that joint adaptation helps only when it starts from a meaningful pre-trained latent space. LU tells a similar story. Joint DTX1 gives the strongest final curve. So trainability by itself is not the win. Useful initial Arrhenius plus joint adaptation is. SIQA is useful because it shows the all-scratch curve does not merely improve slowly, it stays weak and even flattens. The fixed VAE is strong early, but the jointly adapted latent model catches up and finishes among the best.
What configuration do they identify as working best?
Several details matter. During training, a moderate DT block size works best. Block size 16 gives the highest task average at both 30K and 40K checkpoints. At inference, a small number of denasine steps is not enough. The paper says 8 to 10 steps already recover most of the practical gain.
Where are the caveats?
The largest caveat is that generation quality and likelihood style evaluation can disagree. The paper argues that good generation only needs the prior to reach decoder-valid semantic regions, while likelihood estimation also needs accurate local probability calibration around the ground truth posterior neighborhood.
So the result is not simply that latent diffusion beats every language model metric.
Exactly. The stronger claim is narrower and more interesting. With matched to billion parameter baselines and scaling runs up to about 2000 FLOPS, the experiments support hierarchical continuous latent prior modeling as a viable alternative path for text generation, especially when the latent space is pre-grained, jointly adapted, and calibrated.
Then the paper is really arguing for a different decomposition of language generation.
Yes, instead of making one model both plan meaning and emit every token in strict order, CoLIDLM asks a latent diffusion model to organize the semantic plan, then ask the decoder to realize that plan as text. That is the core idea to remember. That wraps up this paper walkthrough.